Let us see the next question on how do we delete a node from binary search tree. Now after we delete a node from binary search tree, the resultant tree should always be a binary search tree. Should again be a binary search tree. Now what do I mean by this? Suppose this is a tree, what I am writing 100, I say 125, here I say 50, 75 and here I say 40. Now if I delete, now there are three cases in which we want to delete a node from binary search tree. The first one is the deletion of the leaf node. Now this leaf node is deleted, there is no dependency on it. The second one is deletion of the half node. Half node means a node which has only one child. And the third one is deletion of the full node. Full node means a node which has two children is called as a full node. Now there are three cases in which we want to delete. Now suppose I want to delete 145. Is there any node called as 145 over there? There is no node 145 with data 145. Therefore we need to say data to be deleted is not found. Okay, now if I say delete 150, you say data is found and deleted successfully. Therefore, there are two return types over here. Return type 0, data to be deleted is not found. Return type 1, data to be deleted is found and deleted. Now, is there a possibility of changing of root? Yes, there is a possibility of changing of root because you might say that delete 100. Now, when I say delete 100, the root data, the root node itself deletes, and what should be the new node, that we will see it in some time. Therefore, how do we write the case over here? I say case, you write read key. Now you have to read the key. Suppose you want to delete 10, 25, 100, 255, anything. Then what do we say? We say m is equal to delete key of ampersand root comma key. Now why it is ampersand root? Because the value of root might change. Now why it is m? Because there are two possible values. Data is found and deleted or data is not found and deleted. Hence we write if m equal 1, data is found and deleted, else data to be deleted is not found, and this is the end of this case. I hope you have understood this case. Please write down this, then we will see one by one how do we delete the key from the binary search tree. Let us write the delete key function. Now in this delete key, the first and foremost thing is we are given with a key. Suppose I want to delete 60. There is no 60 over here and hence we have to say data to be deleted is not found. Now from where we should delete 60? From the root node. And already we have seen how do we search the node. Hence I write struct node star current is equal to star root. Is that okay? Now what do we write over here? We say while current is not equal to null and current arrow data is not equal to key. Now current is not null, yes. Current arrow data is 100 not equal to 60, yes. Now you need to check that 60 is greater than 100 or less than 100. Now how do we write it? We say if key is less than current arrow data. Now what is the value of key? The value of key is 60. Is 60 less than 100? Yes. You move towards the LHS. And what do we write over here? Current equal to current arrow left. Is that okay? Now this is where the current pointer will come to. Now again you go current not null, yes. Current arrow data is 50 not equal to 60, yes. 50 less than 60, sorry, key is 60. 60 less than 50? No. Therefore you need to proceed towards RHS. Hence you say current equal current arrow right. Now when we say current equal current arrow right, the value of current will come to 75. Go back again, current not null, yes. Current arrow data is 75 not equal to 60, yes. 60 less than 75, yes. 60 is less than 75. You say current equal current arrow left. Now the value of current is null. Go back, null not equal null is false. You come out and we check here if the value of current is equal null, the data to be deleted is not found, and if the data to be deleted is not found, we return 0. Is that okay? Now let us say that we want to delete 75. Now if we delete this 75, the right pointer of 50 should be pointing to null. because we are deleting it, and 75 is a leaf node. There is no dependence on it. There are no children of 75. Now since it is a leaf node, if I delete this, the right child of 50 should become null. Now I will have a pointer current over here. I need a pointer to 50 as well, right? Because 50 is parent of 75. That means if I have a parent over here, I can say parent arrow right is equal to null. Are you getting it? Therefore, we need one more pointer, and let us take that one more pointer as parent. Now to begin with, what is the parent of root? There is no parent of root. Therefore, the parent pointer should be initialized to what? Should be initialized to null. Now this is current and the parent pointer is initialized to null. Now current not equal to null, yes. Current arrow data not equal to key, yes. Now we say parent equal to current. Now this is parent is following the current. Now you say parent equal to current. This is where the parent pointer will come to. Now we want to delete 75, 75 less than 100, yes. You say current equal current arrow left. This is where the current comes to. Go back, current not equal to null, yes. Current arrow data, what is it? 50, not equal to 75, yes. You say parent equal to current. Now 75 is greater than 50, therefore you say current equal current arrow right. Go back, current not null, yes. Current arrow data is 75, not equal 75 is false. You come out, is current equal to null? No, the current is not null. Now there are three cases in which we should be deleting, and the first case, you write down, what is the first case? Data to be deleted is a leaf node. What is the first case? Data to be deleted is a leaf node, and this 75 is a leaf node. How do we know that it is a leaf node? It's very simple. We say if current arrow left is equal null, and what do we say? And current arrow right is equal null. Now if the left child is null as well as the right child is null, this is a leaf node. If this is a leaf node, this node should go. This node should go. Now before we delete this node, I need to check, is it on the right side of parent or it is on left side of parent. Therefore, how do we check it? We say if parent arrow right is equal current. What do we write? We write if parent arrow right equal current. Yes, it is parent arrow right equal to current. Therefore, this link should be broken and null should be written over here. And what do we write? Parent arrow right is equal to null. What do we write? Parent arrow right is equal to null. Now this is null. Now it is free to be deleted. This current node can be deleted. Therefore, what do we write? We say free current, and since we have deleted, we can return 1, but we will return 1 at the end. This is the end. Now suppose if you want to delete 40, by the virtue of this loop, if you trace this loop, what will happen? This will be parent and this will be current. Okay. Now is current equal to null? No. Current arrow left is null, current arrow right is null. Yes. If parent arrow right equal to current, is parent arrow right equal to current? No, it is parent arrow left is equal to current. Therefore, I write else if parent arrow left equal current. Yes, parent arrow left is equal current. It means this parent arrow left should be null and this node should be deleted. And that is what we are writing over here. We say parent arrow left is equal to null. Yes, parent arrow left is equal to null, and you say free current, this node will go. Will it work for each and every case? Let us see it. Suppose this is the tree with only one node 10 and this is root and we want to delete 10. Current equal to root, this is current equal to root, parent equal to null, this is parent equal to null, current not equal to null, yes. Current arrow data is 10, key is 10, 10 not equal, 10 is false, you come out. Is current equal to null? No. Current arrow left equal to null? Yes. Current arrow right equal to null? Yes. Now you say parent arrow right equal to current. What is the value of parent? Null. And what is null arrow right? Segmentation fault. Therefore, before this, we need to check if current is equal root. That means the root node itself to be deleted. If current is equal root, now this is a leaf node. only node deleted, the value of root should become what? Null. Hence, what do I write? Star root is equal to null. Now, since this has executed, this should not be executed. We write else if over there, else if and free current. This is the case 1, deletion of a leaf node. I hope you have got this. Next, we will see the second case, deletion of the half node. Please write it down. Alright, I'm not going to explain this loop again and again. This loop will search the element. What does it will do? Suppose I want to delete 150, it will place current over here and it will place parent over there. And pi means parent. We already know that. Please write it down before we see the deletion of the half node. Let us see the second case, deletion of the half node. Now here you have just completed the deletion of the leaf node. Here I write here case 2, deletion of half node. I say deletion of half node. Okay, here I write down else if. Okay. Now what is a half node? A half node is one which has the right child but not the left child, or it has the left child but not the right child. Any one children it has. Therefore, we write if current arrow left is equal null. If the left child is null, what should be right child? Right child should not be null. Current arrow right not equal to null. This is one case. Right? Or what is the second case? If current arrow left not equal to null, then current arrow right should be equal to null. Current arrow right should be equal to null. Is that okay? Now, suppose what is the half node over here? 8 is the half node because 8 has only one child. So, and by the virtue of that while loop, this is where the current pointer is, this is where the parent pointer is. And suppose if you want to delete 8, now is it a half full leaf node? No. Is it a half node? Yes, it is a half node. And if it is a half node, we will delete. How do we delete? That's the question. Now suppose, say for example, before we say deleting of the 8, now this is the root. To begin with, parent is null and this is where the current is. And suppose I want to delete 10 itself. It means current equal to root. Are you getting it? Therefore, we write if current is equal root. Yes, current is equal root. Now, if current is equal to root, if I delete this 10, what should become the root? 4 should become the root. Why 4 should become the root? Because 10 has only left child. 10 may have right child as well, right? Therefore, what do we write over here? If current arrow left not equal to null, then we say root equal to current arrow left. Then what do we say? Root equal to current arrow left. That means this is where the root will come. Or the second thing might be this is 10 and there might be one data 13. This is root and this is the current pointer. To begin with, the parent pointer is null. Now again I want to delete the root. Is it a half child? Yes. Is current equal root? Yes. Is current arrow left not equal to null? No, current arrow left is null. That means current arrow right is not equal to null. Therefore, we write else if current arrow right not equal to null. Yes, current arrow right is not equal to null. Therefore, this is where the root should come to. And what do we write? We say star root is equal to current arrow right. We say star root is equal to current arrow right, and this current we no longer need it. Hence, what do we say? We say free current. We say free current. This is the deletion of the half node with respect to root. Now, is it necessary that the half node has to be root always? No, the half node can be other than root. Say for example, I want to delete 8 now. This is where the current pointer will be. This is where the parent pointer will be. Now, is 8 a half node? Yes. Is current equal root? No, current is not equal to root. That means current is a non-root node. Now, if current is a non-root node, now if I delete this 8, what should be the right child of 4? Right child of 4 should be 6. It should be 6. Therefore, I need to say parent arrow right equal to current arrow left. Why current arrow left? Because current has only the left child. That is what we need to check over there. Hence, we say if, what do I say? Parent arrow right equal current. That means you are deleting on the RHS of parent. You are deleting on the RHS of parent. Parent arrow right equal current. Yes. Now this current might have two children. He has only one children. That children might be on LHS or that child might be on RHS. Therefore, we say if current arrow left not equal to null. Now what is current arrow left? Not equal to null. Yes. Hence we say parent arrow right equal to current arrow left. Hence what do we say? Parent arrow right equal to current arrow left. Hence we say parent arrow right equal to current arrow left. This is the one thing. Or the tree might be this way. And I say 9 over here. And I want to delete 8. 8 is a half node. Is parent arrow right equal current? Yes, parent arrow right equal to current. Is current arrow left not equal to null? The condition phase. It means yes, current arrow right equal to null. If current arrow right equal to null, what shall I say? Parent arrow right equal to current arrow right. What do we write over here? Parent arrow right is equal to current arrow right. Is that okay? Parent arrow right equal to current arrow right. I no longer need this current. Therefore, what do I write over here? I say free current. And this is the end of this else if. This should be else if. Is it okay? Now there is a continuation of this. Now what is that continuation? Suppose this is the tree. Now I say 10, 5, 3, 4. And I want to delete the 3. Now this is the current. Is it a half node? Yes, it is a half node. Is current equal to root? No. Is parent arrow right equal to current? No, parent arrow right is not equal to current. It means, here I am writing the code, else if parent arrow left equal to current. It means what? Parent arrow left is equal current. Yes, parent arrow left is current. Now when I say parent arrow left is current, I need to say parent arrow left equal to current arrow right. Why current arrow right? Because it exists a right child of current. Hence I need to check if current arrow right not equal to null. Yes, current arrow right is not null. Hence I should say parent arrow left equal to current arrow right. Parent arrow left equal to current arrow right. Is that okay? Now this is the one case. Suppose there was 2 over here. Now, is parent arrow left equal current? Yes. Is current arrow right not equal to null? No. It means what? Current arrow left is existing. Hence, what do I write? Parent arrow left is equal to current arrow left. Hence, what do we say? Parent arrow left equal to current arrow left. Now, this is parent arrow left. This is current arrow left. And at the end, we don't need this current node. We say free current. This is the end of else if, and this is the end of this else if. Now the code goes this way. Else if it is root. This is the first part of the code. Now this is the second else if. Else parent arrow right equal current, and this is the third else if. Parent arrow left equal current, and this is the end of half node. This is the end of what? Half node. This is how we delete the half node. Now you pause the video and you write down the code. The next code will be on deletion of the full node. Now let's see how do we delete the full node. Thank you. Let us see the third case in the deletion of a node from BST, that is the deletion of the full node. Now what is a full node? A node which has both the left subtree and the right subtree is called as a full node. Now in this case 75 is a full node, 100 is a full node, 95 is a full node, 90 is a full node because they have two children. And suppose I want to delete 75. Now if I delete 75, what should I replace in place of 75 so that the resultant tree will still be a binary search tree? That's the question. Now what shall we replace in place of 75? If I replace 85 over here, suppose if I replace 85 over here, it is less than 85 and everything are greater than 85 on RHS subtree. Now why only we replace 85? That's the question. Now there is something called as in-order successor and in-order preceder. Before we see this question, what I want to do is we need to check if it is a full node or not. And how do we check it is a full node or not? We say if current arrow left not equal to null, then what? And current arrow right not equal to null. Yes, if the value of left is not null and the value of right is not null, it means what? It is a full node. And if it is a full node, what shall we do? Now what I want to do is I want to write comments over here. Okay, and in this comment, please draw this tree. Yes, pause the video, in comments draw this tree. Okay, you have drawn the tree, and after you draw the tree, there are two definitions, and before the two definitions I want you to write down the in-order traversal of this tree. Now in-order traversal of a binary search tree gives the keys in ascending order. That's what already I said it. Now what is the ascending order over here? 50. What is the next number over here? 70, 75, 70, 75. And what is the next number? It is 85, 87, 90, 85, 87, 90, 92. Okay. Then you write 95, 99, 100, 95, 99, 100, and what is the last number? 125. And this is the in-order traversal of the tree. Is that okay? Now in this in-order traversal, there is something called as in-order preceder and in-order successor. There is something called as what? In-order preceder. Now this in-order preceder and successor are mostly used in many programs when you go to HackerRank and all. Now what is in-order preceder? The number which occurs just before the given number. The number or the node which occurs just before the given number in the in-order traversal is called as in-order preceder. If you want, you write down. I am giving the definition. The node which occurs just before the given node of in-order traversal is called as in-order preceder. Now say for example, if I say in-order preceder of 75, what is this is the in-order traversal. What is occurring just before 75? It is 70. Therefore, in-order preceder of 75 is 70. Now, there is one more definition called as in-order successor. Now, what is in-order successor? Successor means later. The node which occurs just after the given node in the in-order traversal is called as an in-order successor. If I say in-order successor of 75, what is in-order successor of 75? It is 85. It means if I delete this 75, the in-order traversal of the binary tree should give the keys in ascending order. It means either you can replace 70 or you can replace 85. It means either I should get the in-order preceder or I should get the in-order successor. This question I am going to solve by getting the in-order successor. Now what is in-order successor of a given node? How do you find it? It is just after the given node. That means it should be on RHS. It should be on RHS and it is immediately greater. That means it is just greater than 75. Now it means on RHS it is completely towards LHS. Therefore, if this is the node, what you do? You go one step towards right and you go extreme left, you will find the in-order successor. Therefore, how do you find the in-order successor? We say in-order successor is equal to current arrow right. This is in-order successor and you take this completely towards left. And how do we write it? We say while in-order arrow left not equal to null, in-order is equal to in-order arrow left. Now in-order arrow left not equal to null, this is in-order, in-order arrow left not equal to null, this is in-order, in-order arrow left is null. Therefore, you get the in-order successor of the tree. And I want you to close the comments over here. Please pause down the video and write it. Now why we need the in-order successor or in-order preceder? Because if I delete 75 and I replace 85 over here, the tree will be still a binary search tree. I hope you have got this. Please pause the video and write it. Then we will see how do we delete the full node. Okay, please write it down. Now let us see the code for deletion of the full node. We know that we have to find the in-order successor, and we already know how to find the in-order successor. Suppose I want to delete 75 over here. This will be the current node and this will be the parent node by the while loop. Is it a full node? Yes, it is a full node. Therefore, the code comes over here. That is current arrow left not equal null and then current arrow right not equal null. That's the third case. And the final case, deletion. Now, if it is not null, I need to find the in-order successor. Now, what is in-order successor? It is 85. Now, this 85 should come in the 75th place. Now, if I take this 85 in the 75th place, right, what should be the right child of 90? It should be 87. It means I need a parent pointer to in-order successor. Therefore, what do I write over here? I say struct node star in-order successor. And from where do we start? We start from current arrow right. We start from current arrow right. And what should be the I need a parent, right? Parent of in-order successor. Why I need it? Because if I take 85 to 75 position, the left child of 90 should be 87. And why only for the 90? Because it is parent of 85. And initially, what do we say? We say temp is equal to null. Temp is nothing but the parent of in-order successor. And what do we write? We say while in-order arrow left is not equal to null, the parent should go along with the in-order successor. Temp is equal to in-order successor, in-order equal to in-order arrow left. Is that okay? Now, in-order arrow, now this is in-order current arrow right. In-order arrow right left not equal to null, yes. Temp equal to in-order equal to in-order arrow left. In-order arrow left not equal to null, temp equal to in-order equal to in-order arrow left. Go back, in-order arrow left not equal to null, the condition fails. Now you come out. Now, this, the right left child of 90 should be 87. Therefore, we say temp arrow left equal to in-order arrow right. That is what I need to write. Therefore, we write temp arrow left is equal to in-order arrow right is equal to in-order arrow right. Is that okay? Now, this in-order arrow left should be pointing to 70. And how do you get 70? You say current arrow left. Therefore, in-order arrow left equal to current arrow left. That is what I write. In-order arrow left equal to current arrow left. Is it okay? And what should be the right child of 85? The right child of 85 should be 95. And how do you get 95? Current arrow right. Therefore, in-order arrow right equal to current arrow right. In-order arrow right is equal to current arrow right. Is it fair enough? In-order arrow right equal to current arrow right. Now, it means as good as if I redraw the diagram, this 85 is being taken up and the left child is 70 and the right child is 95. Now, who should be the parent of 85? 50 should be the parent of 85 because 50 is the parent of 70. Now, this child 75 might be on the right side or might be on the left side. That is what we need to check over here. And we write if parent arrow right equal current. Is parent arrow right equal current? Yes, parent arrow right is equal to current. Therefore, we say parent arrow right equal to in-order successor. Therefore, what do I write? Parent arrow right equal to in-order successor. Similarly, this 75 would have been on the LHS if it was 25. It would have been on LHS of 50, right? It means, therefore, I need to write one more condition, else parent arrow left equal current. Now, if parent arrow left equal current, what shall I write? Parent arrow left equal to in-order successor. Is that okay? Now, this link is established. Now, we no longer need this current. Therefore, I say free current. Therefore, I say what? Free current. Okay, this is the end of this else if. And since the node is being completely deleted, what do we say? We say return 1 and this is the end of the function. Is that okay? Now, will it work for each and every case? That's the question, and we will answer this question in some moment. Right? And we will see when does this code doesn't work. Suppose this is the tree. 10, 25 and 5. Okay, 10, 25 and 5. And I want to delete 10. This is current, this is root, parent equal to null. Now, is it a full node? Yes, it is a full node. In order equal to current arrow right, in order equal to current arrow right. And what is the value of temp to begin with? It is null. In order arrow left, what is in order arrow left? Null. Do not execute this. Temp arrow left, null arrow left is segmentation fault. Therefore, this has to be done only if the value of temp is not equal to null. Now, temp is null, null not equal to null is false. In order arrow left equals current arrow left. Now, you take current arrow left. What is current arrow left? 5. Where do you store in order arrow left? This is the way you store. Now, 25, the left child of 25 is 5. In order arrow right is current arrow right. Now, what is in order arrow right? This is the place in order arrow right. What you want to store? Current arrow right. What is current arrow right? 25 itself. That means you are getting a self loop. Do you need a self loop? We don't need a self loop. When we don't need a self loop, if the right child itself is the in order successor. And how do we know that the right child itself is in order successor? If in order equal current arrow right. If it is not equal to current arrow right, then only we have to make this thing. Now, this is in, this is current arrow right is 25, in order is 25, 25 not equal to 25 is false. You come here. Parent, what is the value of parent? It is null. Null arrow right is segmentation fault. Now, if parent is null, it means it is a root. Therefore, we say if current is equal root. Yes, current is equal root. Now, if current is equal to root, now what should become root? This in order successor should become root right. Therefore, what do I write? Star root is equal to in order successor. Now, this should be else if you just write else, this should give segmentation fault, because even though this condition is true, this will be executed if you would have written if. Therefore, else if. Now, you say free current means this is free current is gone. Right, and you say return 1. If I redraw this tree, it is 25, 5, and this is where the root will be. This is how we delete a full node from the binary search tree. And the assignment will be, the first assignment, you have to find max node in BST. Now, what is the maximum node in this BST? It is 25. Now, if I write 30 over here, it is 30. You go towards the extreme right, you will find the max node, and the second assignment is find the min node in the BST. This is what we have done in the today's class, and in the next class we will solve the many more examples. Thank you.